Aitkens delta squared method based on this formula here. P sub n hat equals P sub n minus delta Pn squared over delta squared Pn. And these are different things. What do they represent and what is the setting here? In this formula, we are given a sequence Pn. Typically, we'll let the subscript n start at 0, and we're imagining it going up to infinity. For that given sequence, we can create new sequences. Delta P sub n, by definition, is a symbol that represents a new sequence that is formed from this old sequence by taking differences. Change in function values, you could say. It's P sub n minus P sub n minus 1. And this formula is valid. Oh, you know what? I got it wrong there. And that's bad, actually. It's P sub n plus 1 minus P sub n. The formula I wrote down is not quite the same thing. I want to use this formula for n equals 0, 1, 2, 3, etc. So I'm getting a new sequence that you could write this way. That's a new sequence. I could apply the delta operator to that sequence as well. I could compute delta of Pn. Or hey, why don't we just call that delta squared for short? This is like a first derivative, and this is like a second derivative. I'm already talking about discrete calculus here. So if I think of it this way, delta of Pn, according to this kind of idea up here, it must be delta of Pn plus 1 minus delta of Pn. For n equals 0, 1, 2, 3, etc. It's like this idea up here, except I've got the deltas in there. But what is delta P sub n plus 1? According to this, replace all n's with n plus 1. This must be P sub n plus 2 minus P sub n plus 1. And then this one must be the same thing you see up there, P sub n plus 1 minus P sub n. Simplify that, you're going to get P sub n plus 2 minus 2 times P sub n plus 1 plus P sub n. All this is right here is just shorthand notation for that. What I just circled there. Perhaps it would have been better to put that over here, defining this notation. Effectively, like I'm defining a second derivative by taking the derivative of the derivative. But this is a discrete derivative, not continuous derivative. It's discrete calculus. If you plug these things in to this formula up here, that one in that spot, and this one in this spot, you get the other formula that's in the book at the top of page 87. This formula up here. That again is derived on the previous page and whose derivation you don't need to know. What's the idea? Why in the world are we doing this? Again, the title of this section is Accelerating Convergence. This theorem says when you have a sequence that converges linearly to some number p, and if this inequality is true, then the Aitkens delta squared sequence converges to p faster than the original sequence in the sense that this limit is 0. So the numerator is converging to 0 faster than the denominator is here. That makes sense? This does not necessarily imply that Pn hat is converging quadratically to P, just faster than Pn. We're not going to prove this. In fact, the book doesn't prove this. Let's just get a little feel for what's going on by implementing this in a spreadsheet. Let's apply it to a situation we're already familiar with, trying to estimate a solution of the equation cosine of x equals x. What was the solution of that equation again? It was close to 0.7, 0.739085. Actually, if you want more decimal places of accuracy with fine root, you can do comma working precision O arrow 10 and get more decimal places of accuracy. 0.73908513332 is our, what would that be? 10 decimal place approximation to solution, which was a unique solution actually, unique solution of cos x equals x. The answer to 10 decimal places, not places, but places, we see from Mathematica's fine root. And by the way, you should know fine root, solve and nestless syntax for the test as well, if I ask you to write those things on the test. 0.73908513332. Let's make a table of different sequences based on things we know, how to approximate solutions of this equation. So I'm going to have a column for n, starting with 0 and just going up by 1 each time. This is just the subscript. I think you all use spreadsheets enough to know you can do that kind of thing here. Copy and paste this down. How far? Oh, I don't know. How about 20 spots? So we'll compute up to P20. What's the first way we learn how to find, in this case, fixed points, which this can be converted to a root finding problem, right? You could create a new function, f of x is cosine of x minus x. By the way, when I talk this way, I'm reviewing for the exam. This was one of our main topics. I could take this equation, cosine of x equals x, and that's a fixed point problem, and convert it to a root finding problem by letting f of x equal cosine of x minus x. And I could use the bisection method as our first method for estimating the root of that equation, which will be the fixed point of this one. Simpler method is just iterating the function cosine of x itself. Let's do that. Well, we need an initial guess. How about 0.7 again? That'll be p sub 0. I'm just plugging the previous number into the cosine function. That's all I'm doing. So in a spreadsheet, I can type there equals cosine of, in this case, B4 is where P0 is. And if you copy and paste that formula downward, that's just going to keep iterating the cosine function. Of course, on a TI calculator, you just keep hitting enter after you've used the answer feature. Remember what we're trying to converge to, 0.739085. How close are we by 20 iterations? You may say not too bad, though that's definitely slower than Newton's method is. Yeah, this should feel more slow than you might hope for. With Newton's method, you're typically pretty close by 4 or 5 iterations. Here we're not. Let's review error as well. The error, approximation error, is the approximate value minus, the actual value minus the approximate value. And I corrected myself there because, remember, it goes in alphabetical order. Actual minus approximate. So I take the actual value here, which is in cell F1, and subtract the approximate value here in cell B4. Although if I'm going to copy and paste this, I'll need to use my dollar signs to keep the cell reference fixed. I think most of you know about all this kind of spreadsheet stuff. No? The dollar signs there around the F keep that cell reference fixed as I copy and paste the formula downward. Okay, spreadsheet use will not be required on the exam, so I will re-emphasize these things after spring break.
What was the formula for PN, the first one?
I just picked 0.7 as my seed.
Oh, okay, yep.
So the dollar signs, again, that doesn't mean money here. It keeps that cell reference F1 fixed as I copy and paste downward. B4 does not have dollar signs around it. So that will get updated to B5, then B6, then B7 as I click and drag. In fact, it already autofills. But I like clicking and dragging to emphasize. Those are the errors. This first error is positive because this is too small. Actual minus approximate is positive. The second error is negative because this is too big. Actual minus approximate is negative. The absolute errors could be found as well. Get rid of the minus signs. And if you got rid of all those minus signs, you see the error is going towards 0, but more slowly than you might hope. In effect, to me, it looks like the absolute error of each estimate is going down by a factor of about 2/3 maybe every time, from about 0.012 to about 0.008, for example, to about 0.0053. Effectively, if you get rid of those minus signs, it's like you're multiplying by 2/3 every time. It is like a geometric decay to 0, which we've always called fast before this class, right? Geometric or exponential growth and decay are fast growth and decay before this class. But in this class, we called these things linear convergence. Not so fast, actually, compared to things like Newton's method, which is more quadratic typically. So we're after faster convergence in this class. So what's the goal here now? The goal is to accelerate the convergence of this sequence according to Aitkens' delta squared method. Let's go ahead and make a new column that we could call delta Pn. Symbolically, if I'm writing it by hand, capital delta P sub n. It's a new sequence. Again, its formula is right there. So delta P sub 0 would be P1 minus P0. Delta P sub 1 would be P2 minus P1. Delta P2 would be P3 minus P2. Pn plus 1 minus Pn. Delta P0 is P1 minus P0. B4 minus B5. Click and drag that formula down, it'll get updated correctly. So this number right there, delta P1, is P2 minus P1, which is a negative number. So this is a new sequence that's kind of like the derivative of the original sequence, a discrete derivative. It is somehow measuring a rate of change, you could say, of the original sequence. The fact that this first one's positive, about 0.06, means initially the original sequence is going up by about 0.06. Hey, that's why you want that error to be positive there. Or the difference to be positive is you want to consider that to be a change in the function value. The next delta P1 is negative, so the function goes down. It's measuring the rate of change, a discrete rate of change. How about delta squared Pn? There's two ways I could do the formula. One way is to think of it like that right there. Take the sequence, who's the column that I just made, and apply the same idea. Another way is to think of it that way, the simplified form in terms of the original sequence. Let's do it both ways and see that we get the same thing. So if I think of it as a new sequence generated by doing the derivative of the first derivative, so to speak, do this. It's like the second derivative of the original function. By the way, I don't know if you noticed when I went copied and pasted down here, I did not go in this column all the way to that spot because this spot's not filled in. And in this column, I only want to go to this spot because that spot's not filled in. So there are the delta squared Pn values. Let's check that P sub n plus 2 minus 2 times P sub n plus 1 plus Pn, using parentheses here as my subscripts, gives the same thing. So I'm going back to the original column B here. P sub n plus 2 is right there, minus 2 times P sub n plus 1 plus P sub n. That's the same. That's the same. Yep, looking good. So I could use either approach. It's probably more convenient for spreadsheets, at least, to use the first approach. In fact, I could have copied and pasted the formulas from this column to this column instead of retyping it. And since the new column was the new, it probably wouldn't work, excuse me, because Pn is 2 columns away from delta Pn, whereas this one is only 1 column away from this one. So it wouldn't have quite worked. But if I did not have this error column, I could have done that. Not quite done. Remember, Aitkens delta squared method ultimately is to use this equation to get a sequence that's supposed to converge to the same number, root of cosine of x equals x, but faster than the original sequence. So there's what I'm about to use here. Can you remember it? Pn minus a fraction delta Pn squared divided by delta squared Pn. So this is Pn hat. This is the Aitkens delta squared method. Aitkens delta squared sequence, I'll call it. Pn hat, this is what I'm after. So again, take Pn minus a fraction, where the top was Pn squared, delta Pn squared, excuse me, and the bottom was delta squared Pn. See what I'm doing there? I'll redo it here. Redo it again, just to reemphasize things. So Pn is in column B, okay. So I took Pn minus delta Pn squared divided by delta squared Pn. I'm squaring the numerator and I'm not squaring the denominator, because the denominator is a new column. Hey, it's already close to 0.739 after just a couple iterations. What's the error? Yeah, we're already pretty close to it's not quite as fast as Newton's method, but it is faster than the original example. Whether the errors here, make another column for the errors. Take the actual value in F1, subtract these approximate values. Now these errors are always positive. I wasn't necessarily expecting that. And they are getting pretty small pretty fast. I mean, the first one is already very small. Go down by a little bit more than a half to get from there to there, a little bit more than a half to get from there to there. And it's not clear that the factor is going down by much more than a half each time, maybe a little bit more. But I mean, it's definitely already closer to 0 to start with. It's clearly faster convergence. Is it truly fitting the theorem in the book? That's not obvious. The theorem in the book saying this is true, which again, be able to read this limit statement. What does it mean intuitively? If the limit of this fraction is 0, means the top is going to 0 much faster than the bottom. Both the top and the bottom are going to 0, by the way, because I'm assuming Pn is going to 0. And at least if the theorem is true, Pn hat is also going to P, so this is going to 0. Or the top is going to 0. Both of these numerators and denominators are going to 0. But because the limit of the fraction is 0, that means the top is going to 0 somewhat faster than the bottom, intuitively. But not enough, evidently, to imply necessarily quadratic convergence. Not going to test you on Steffensen's method. But let's see if we can implement Steffensen's method in a spreadsheet at least. The hardest part about Steffensen's method is the notation. I'm going to ignore the notation down here with all the superscripts and just focus on this idea up here and what the book describes here in this paragraph. With Steffensen's method, you got your initial guess, P0. You plug it into G, which is the cosine function, to get P1. Cosine function for our example. Plug that into G again, cosine function again to get P2. Then you take those three numbers, P0, P1, and P2, and apply Aitkens' delta square method to get a new number. This delta squared in the curly braces represents Aitkens' delta squared method. Saying applied to P0, but you're really applying it to these three numbers. Then what's new here, or what's weird, is you then, okay, this is Aitkens' delta squared method. You then, Steffensen's method constructs the same first four terms. However, at the next step, assume P0 hat is a better approximation to P than P2 is. So apply fixed point iteration, the function G, to P0 hat instead of P2. It's almost like it's more like it's a mix of fixed point iterations and Aitkens' delta squared method. So it's sort of extra confusing that way. And I guess I'm not going to test you on it, but what is this all saying to do? Let me just quickly summarize it in the spreadsheet. So the Steffensen's method, I'm not going to use the book's notation here. I'll just call this column estimates. Again, you can use the same P0, the same 0.7 as we started with. It's going to be different than Pn hat initially. We're then just plugging that into the cosine function, like we did with the first approach. That was the slowest approach. And then we apply Aitkens' delta squared method to this. So the fourth or the third iteration here, this number that I get here should be the same as this number here, Pn hat 0 or P hat 0. How am I going to apply it? Let's say we do this minus, okay, if I'm not using these columns, I need to do, let's see, it was this minus this squared, that's delta Pn quantity squared. I'm using more parentheses than I need to here, but divide by delta squared Pn, that would be this number, track with me here, minus 2 times this number, plus that number. This number, minus 2 times this number, plus this number. Yeah, this is the same as that. Say it again, watch. This is the same as that. So it seems like we're going slower at first. But if we now apply the cosine function here by copying and pasting this down here and apply it again, and then do the same copy and paste this one down here like this, we're already very close to the true root here. 0.739085. Yeah, look at that, 0.739085, even faster than Pn hat. And I can just keep copying and pasting in groups of 3 here if I like. And already by this point, we're to, that's as many decimal places as Mathematica had of accuracy.